So far in this unit, we have actually been able to figure out what certain types of series actually converge to. It turns out that often it is the case that figuring out what number a series converges to is not possible, and what you need to do instead is just determine if the series converges, and then you use a partial sum to estimate the value that it will converge to. So we will have a whole bunch of tests that will allow us to determine if a series converges or diverges. And the first one is called the integral test. And this will allow us to determine whether a whole class of series called P-series will allow us to tell very easily when certain types of series converge or diverge. So how might you use an integral to determine whether the sum from n equals 1 to infinity of 1 over n squared converges or diverges? This becomes pretty obvious if you draw a picture. So draw the function 1 over x squared. So f of x equals 1 over x squared. It goes through a point 1, 1, and then it decreases as x goes to infinity. It decreases much more quickly than that, but if I draw the picture decreasing too quickly, it makes it hard to draw my boxes. Okay, so then this is x equals 1, this is x equals 2, there's x equals 3. So now look at that. That has an area of 1. This next box, the height is 1 over 2 squared. So its area is 1 over 2 squared because the base is 1. The next box will have area 1 over 3 squared. And when I input 4, that box will have an area of 1 over 4 squared. And so what you can tell from this, so what you should notice, is that the sum from n equals 1 to infinity of 1 over n squared, that's less than or equal to the area under this curve. So the integral from 1 to infinity of 1 over x squared dx plus an additional 1 for the area of this box. So the sum of your series is less than or equal to this thing. And if you can determine that this integral converges, well, then it sort of seems logical that this series probably converges too because it's smaller than a convergent something. So let's evaluate that infinite integral. This is the limit as the sum b goes to infinity, the integral from 1 to b, x to the negative 2 dx, plus that 1. So now the antiderivative of x to the negative 2 is negative x to the negative first. And that will be the limit as b goes to infinity, negative 1 over b plus 1 over 1 plus 1. So this gives us that the sum is less than or equal to 2. Okay, so what that tells us then is that the sequence of partial sums, so thus Sn, is bounded above by 2. And the other thing that you can notice is that the sequence of partial sums, those Sn's, this is increasing. And the reason it's increasing is that each time n increases, as in you add up more things, you add on a positive term. And those things together, a sequence that's bounded and increasing, it will converge by that monotonic sequence theorem back from section 11.1. So thus, the sequence of partial sums, Sn, converges by the monotonic sequence theorem. Now what the important thing to notice here is that the behavior of your sum was convergent, and so was the behavior of the integral of sort of the an's summed inside of an integral sign instead. So the sum and the integral seem to do the same thing. So how might we use an integral to determine whether or not this sum converges or diverges? So we set up sort of a similar picture, and it looks awfully similar to the previous picture, it just doesn't decrease as quickly. So there's the function f of x equals 1 over root x. And here's 1, here's 2, here's x equals 3. And this time, instead of doing right sums, we find the left sum. So there's an overestimate. Okay, now the area of this first box will be 1 over root 1. The area of the second box will be 1 over root 2. Third box, 1 over root 3. And so from the picture, you can see that the sum from n equals 1 to infinity of 1 over root n, that's bigger than or equal to the integral from 1 to infinity of 1 over root x. And the thing you can also notice is, well, if this integral is infinite, then that series must be infinite too. So the integral from 1 to infinity of 1 over root x dx, that's the same thing as the limit as b goes to infinity, integral from 1 to b, x to the negative 1/2 dx, which is the limit as b goes to infinity to x to the 1/2 evaluated from 1 to b, or is the limit as b goes to infinity to root b minus 2, which will be infinite. So you know that your sum is larger than something that is infinite. That means that your series has to also diverge. So thus, the series diverges. But as before, the main pattern you have to understand here is that the sum and the integral do the same thing. So the sum from n equals 1 to infinity of 1 over root n does the same thing as the integral from 1 to infinity of 1 over root x. And that is the basis of the integral test. You do have to assume a few things. So you have to suppose that your function f is continuous, positive, and decreasing. If one of those pieces is broken, this test will not work. And you say that's true on the interval from 1 to infinity. That part's a little bit flexible. It can also be different intervals. We'll talk about that in a little bit. And you also assume that the nth term of your sequence is obtained by plugging in n into your function. And what this test says is that your series is convergent if and only if the improper integral is convergent. So what that means is if your integral is convergent, so is your series. If your integral is divergent, then so is the series. So the integral and the series do these same things in terms of convergence and divergence. We are actually going to prove just the first case, and the second case is quite similar. So let's prove case 1. Okay, so what we're going to show is that if the integral from 1 to infinity of f of x dx is convergent, then so is the sum from n equals 1 to infinity of an. Okay, so the picture is pretty much the same thing that we had for the whole 1 over x squared example. You have some positive decreasing continuous function, y equals f of x. Here's 1, 2, 3. Okay, so once again we construct boxes. We do a right estimate. Now the area of this box will be a2, the second term. This one will be A3, the third term. The next box will have area A4. Remember, the reason that is because when you plug in 4, you get that the y value here is f of 4, which we've assumed equals the fourth term that we're summing up. Okay, now the first thing to notice is that if we show the sum from n equals 2 to infinity of an converges, so does the sum from n equals 1 to infinity of an. All you do there is add on one more term, and that one more term is going to be a finite number. It will not affect the convergence or divergence. What we're going to do is we're going to let s sub n equal our nth partial sum. So that's the sum from I equals 1 to n of ai. So you just need two variables there because you need that n on the top to equal the number of things you've added up. Okay, and then from your picture, you can observe, just like we did with the 1 over x squared, that your Sn, which is a1 plus a2 all the way up to an, that's less than or equal to a1 plus the integral from 1 up to n of f of x dx. And one thing to note here is that this inequality depends on f of x being a decreasing function. And let's talk a little bit about why that's true. So first of all, the integral from 1 to n would be the area under the curve from here to up to, say, whatever that n is. And you can see that those boxes, a2 up to an, are going to fall underneath your curve. The fact that those right endpoint estimates are underestimates depends upon the fact that that curve is decreasing. If the curve was increasing, they would be overestimates. So you need this decreasing to ensure that the inequality goes in this particular direction. Okay. And the other thing to notice is that an integral from 1 to n is certainly going to be less than an integral from 1 to infinity. So what you can also observe is that Sn will be less than or equal to a1 plus the integral from 1 to n of f of x dx, which is less than or equal to a1 plus the integral from 1 to infinity of f of x dx. And because you know that this thing converges, this is less than or equal to some number m. M might be huge, but it's less than some number. And what this tells us is that the sequence of partial sums Sn is bounded. And then the other thing is, as the terms an are positive, the sequence of partial sums is an increasing sequence. What you have to keep straight there is that Sn is the sum of n things. So as the n increases, you add more and more things, and if you're adding positive things, this sequence of partial sums will be an increasing sequence. And so thus, the Sn converges. You don't know what to, you just know that it converges. And the sequence of partial sums converging, this means the series converges. The proof for divergence is pretty similar to the proof for the 1 over root n diverging. The basic idea that you really have to get here, the most important take-home message from this, is that the integral and the sum do the same thing. So the integral series, they behave the same way. Okay, a couple notes about the integral test before we actually apply the integral test. So a big part about the integral test is you have to check that the conditions are met before you apply it. So you always have to check, is your function continuous? And you should tell me like on which interval. You have to show that the function is positive, and also probably state on which interval. And then it also is important to show me that the function is decreasing. You have to establish those things before you even apply the test. So the first thing that's not necessary, your series doesn't necessarily have to start at n equals 1. Some series might start at n equals 2, in which case you'll just take your improper integral from 2 instead of 1. So for example, maybe I gave you the series, the sum from n equals 2 to infinity, 1 over n ln of n. Having that series start at 1 will not work because ln of 1 is 0. So if you were given this series, when you're trying to establish convergence or divergence, just use the integral from 2 to infinity of 1 over x ln x dx. So that's the first thing. Don't have to start at 1. The second thing is it's not necessary that the function f be always decreasing. What's important is that it has to eventually or ultimately start decreasing. So if you have some function f of x, and if x is greater than or equal to 3, f of x decreases. That's totally fine. And to establish decreasing, you may have to use f prime. And remember, from calculus 1, a function is decreasing if f prime of x is negative or less than 0. There are some instances in which you can say that the terms are obviously decreasing. So I think that that's really only the case when the variable is in the denominator only, and the functions in the denominator are increasing. So for example, if I gave you f of x equals 1 over, I don't know, x times ln of x, you know that as the x's in the bottom increase, so as you know, as x increases, you know that x times ln of x is less than x plus 1 times ln of x plus 1. And so therefore 1 over x ln x is bigger than 1 over x plus 1 ln of x plus 1. In that case, you can say something is obviously decreasing. You cannot say things are obviously decreasing when you have variables in the numerator and denominator. In this case, you should use a derivative. Okay, so let's actually apply an integral test. So apply the integral test to the series 2 over n squared plus 1. So start by defining your function. Let f of x equal 2 over x squared plus 1. And then you can say, okay, well, note that the function f of x is continuous and positive on the interval from 1 to infinity. It's continuous and positive on more than just that interval, but that's the part you care about because your series goes from 1 to infinity. Also, f of x is decreasing. You can show this using a derivative if you want to, and that's actually not true all the place, but it's decreasing for x's that are bigger than or equal to 1 for sure. If you were to use a derivative, the derivative of this function, f prime of x, would equal, so that's 2 times x squared plus 1 to the negative first. So the derivative is negative 2 times x squared plus 1 to the negative second times 2x, which is negative 4x over x squared plus 1. This is less than 0 so long as x is bigger than 0. If x were a negative number, then this derivative would be positive. But we only care about positive numbers because our series goes from 1 to infinity. Okay, so we're going to apply the integral test. So we're going to find the integral from 1 to infinity of 2 over x squared plus 1 dx. And if this integral converges, so will our series. If this integral diverges, so will our series. So that's the same thing as the limit as b goes to infinity, integral from 1 to b, 2 over x squared plus 1. The antiderivative of 2 over x squared plus 1 is 2 arctan of x. So that's the limit as b goes to infinity of 2 arctan b minus 2 arctan 1. And as b goes to infinity, arctan goes to pi over 2. 2 times pi over 2 is pi. And arctan of 1 is pi quarters, so minus pi halves, which is pi halves. So your integral converges. And let's write me a short sentence that gives me a conclusion. So as the integral from 1 to infinity of 2 over x squared plus 1 dx converges, the series, the sum from n equals 1 to infinity 2 over n squared plus 1 also converges by the integral test. You will be learning lots of names of tests in this unit, so please actually state which test you're using. It's kind of redundant in this section because this section is just the integral test. But in the next sections we will have other tests that you'll have to use, so it's just best to refer to them by name. Let's apply the integral test to another function. So start by defining your function. Let your function f of x equal x over x squared plus 4. Okay, first thing to note is note that f is continuous and positive on the interval from 1 to infinity. You do have to specify that interval from 1 to infinity because technically if you didn't say that, you'd be saying this function was positive everywhere, which is actually not true. It's not positive for negative x's, it's only positive for positive x's. Okay, now to establish decreasing, let's use a derivative. So f prime is equal to the lower function multiplied by the derivative of the upper function minus the upper function times the derivative of the lower, all over the lower function squared. And that will simplify to 4 minus x squared over x squared plus 4, the quantity squared. Now this thing will be less than 0 if x squared is bigger than 4, or for us, that's true if x is bigger than 2. So your function f of x is decreasing on the interval from at least from 2 to infinity. And remember that ultimately decreasing was sufficient. So we're going to apply the integral test. So find the integral from 1 to infinity, 1 over x squared plus x over x squared plus 4 dx. So that's the same thing as the limit. B goes to infinity, 1 to b, x over x squared plus 4 dx. Now we're going to make a substitution. I know it's weird, but your bounds become weird changed things. So if you let u equal x squared plus 4, du equals 2x dx. We're going to have a 1/2 in there. If x equals 1, then u becomes 5. And if x equals b, then u becomes b squared plus 4. I know it's weird, just live with it. Limit b goes to infinity, 5 to b squared plus 4, 1/2 times 1 over u du. It's really not that bad once you get used to it. All right, the antiderivative of 1 over u is natural log absolute value u. From 5 to b squared plus 4. So that's the limit as b goes to infinity. 1/2 natural log absolute value b squared plus 4 minus 1/2 natural log absolute value 5. And as b goes to infinity, this first term is going to go to infinity as well. So this integral diverges. And let's just say as the integral diverges, so does the series by the integral test. And as you can see, most of the work in these questions is establishing that you can actually do the test and then carrying out the integral itself. Okay, confirm that the integral test can be applied to this series. And then let's use it to determine the convergence or divergence. So first, let's define our function. So e to the 1 over x squared. Note that f of x is both continuous and positive on the interval from 1 to infinity. This function is continuous as long as your x isn't 0, and it is actually positive for every value at which it's defined. We have to show decreasing, and since I think it's not really obvious, we're going to use a derivative. Okay, so also f prime of x, so use the quotient rule. So lower x squared times the derivative of the upper. The derivative of e to the 1 over x is e to the 1 over x times the derivative of 1 over x, which is negative 1 over x squared, minus the upper function times the derivative of the lower function, all over that lower function squared, which will be x to the 4th. Notice how this x squared and that x squared are going to cancel. Also, there's a greatest common factor of e to the 1 over x. So e to the 1 over x times negative 1 minus 2x all over x to the 4th. Or I guess you could have factored that negative out, made it negative e to the 1 over x, 1 plus 2x over x to the 4th. Okay, now negative e to the 1 over x times 1 plus 2x, that's going to be less than 0 if, let's solve that. Dividing by e to the 1 over x is totally okay because it's a positive quantity, it's non-zero. So we have negative 1 plus 2x is less than 0, which means 1 plus 2x is greater than 0, dividing by negative 1. 2x is bigger than negative 1. X is bigger than negative 1/2. So as long as our x is bigger than -1/2, our series is decreasing. So this is certainly true if x is bigger than or equal to 1. So thus f is decreasing. So let's apply the integral test. Actually integrate now. So the integral from 1 to infinity, e to the 1 over x squared dx. That's the limit as n goes to infinity, b goes to infinity, let's say. 1 to b, e to the 1 over x squared dx. Once again, this is a u sub, so we're going to let u equal 1 over x. The derivative of that is -1 over x squared dx. If x equals 1, u will equal 1. And if x equals b, u is 1 over b. So this becomes the limit as b goes to infinity, the integral from 1 to 1 over b, negative e to the u du. So that's negative e to the 1 over b plus e to the 1. And as b goes to infinity, that 1 over b is going to go to 0. So we have negative e to the 0 power plus e to the first, which is e minus 1. So the integral converges to e minus 1. And so thus, as the integral converges, so does the series by the integral test. All right, let's confirm the test can be applied to this one. Now notice that on this one you get a little bit of a break. You only have variables in the denominator, and both n and ln of n squared are increasing, so which means as n gets large, the denominator gets larger, so the overall function gets smaller. This is one of those cases you can just say that your function is obviously decreasing. So first, let f of x equal 1 over n times ln of n squared. Note that your function f of x is continuous, positive, and decreasing. Specify that that's true on the interval from 1 to infinity, or 2 to infinity, excuse me. This function is actually not defined at 1. Okay, so apply the integral test. So then the integral from 2 to infinity of 1 over x ln of x, the quantity squared, dx. That's the same thing as the limit as b goes to infinity, 2 to b, 1 over x ln x squared dx. Okay, substitute again. We're going to let u equal ln of x. Du is 1 over x dx. If u is equal to, that's if x is equal to 2. So if x equals 2, then u will equal ln of 2. And if x equals b, u equals ln of b. So our integral becomes the integral limit, forget that, as b goes to infinity, ln 2 to ln b. Inside the integral is just u to the negative second du. So that's the limit as b goes to infinity, negative u to the negative first, evaluated from ln 2 to ln b. So negative 1 over ln b plus 1 over ln of 2. And as b goes to infinity, 1 over ln b will go to 0. So this improper integral converges to 1 over ln of 2. So as the integral converges, so does the series by the integral test. Now, we are going to use this quite often. So we have certain series that are pretty special, and they're called p-series. So a series of the form n equals 1 to infinity 1 over n to the p is called a p-series. And this p-series will converge if your p is greater than 1 and diverge if it's between 0 and 1. And this is related to what we learned in an earlier section about improper integrals. So if we had an integral from 1 to infinity 1 over x to the power of p dx, this thing converged if that power p was strictly bigger than 1, and it diverged if p was less than or equal to 1. So that allowed us to look at certain integrals and very quickly determine what was happening, like 1 to infinity 1 over x squared dx. That converges. To figure out what 2, you gotta do some more work, but you just know that it converges. The integral from 1 to infinity of, say, to infinity of 1 over x dx, you can say right away that that thing diverges. So you can use this theorem to just say something, a series converges or diverges without doing any work at all. Just tell me it's a p-series and tell me what p is equal to. So for example, this for series A, that's the harmonic series, it's also a p-series. So this diverges as it is a p-series with p equal to 1. This next one technically is the sum from n equals 1 to infinity 2 over n to the 3/2. So it's a p-series with p equal to 3/2. Therefore, this series converges. And this one is a p-series with p equal to 2/5. Since that's less than 1, this series diverges. You could, say, apply the integral test to all of these functions. What I'm saying is that you can just tell me they're a p-series, you don't have to. Now the next question is if we know a series converges, we might want to estimate what it actually sums up to. So we know a series converges. We want to estimate the actual sum, which we're going to call S, with a partial sum, Sn. And the question is, how big should n be? Should we add the first 100 terms, the first 1,000 terms, the first 10,000 terms, just the first 5? So we're going to get a bound on the remainder of that sum. Okay, so once again, those pictures like we drew before come in pretty handy. Okay, so assuming we're at some number n where we stop counting, you have this continuous positive decreasing function. Here's n, here's n plus 1, here's n plus 2. Plus 3. Okay, so what we want to do is we want to estimate Rn which is the remainder, or what we've left off. Okay, so if you take the sum S, which is the actual total sum, and you subtract off the first n things, that will give you an plus 1 plus an plus 2 up to all the rest of those terms. So if you took off the first n things, you start adding from n plus 1 up to infinity. And from this picture that I drew, you can see that an plus 1, that's the area of this box, plus an plus 2, that's the area of this next box. All that's going to be less than or equal to the integral from n to infinity of f of x dx. And that's because the integral from n to infinity is the area under this curve, and that area is greater than the area of just those boxes. So that gives us an overestimate for the remainder. And if we draw another picture, we can figure out what an estimate for the lower bound on the remainder is. So here's n plus 1, n plus 2, n plus 3, same sort of idea. Okay, and also your remainder, an plus 1 plus an plus 2, etc., all those things added up, it's going to be bigger than or equal to an integral from n plus 1 to infinity of f of x dx. And just note that n is the number that you sum to. So here's that in summary. So if you have a continuous positive and decreasing function and you apply the integral test, you know that your series is convergent. The remainder, or how much you are off from your actual sum by, is in between the integral from n plus 1 to infinity of f of x dx and the integral from n to infinity of f of x dx. Okay, approximate this sum by using the sum of the first 10 terms. So that will be S10, which is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared up to 1 over 10 squared. I don't want you to actually do that arithmetic, so please don't. Just use a calculator and tell me what that's approximately equal to. It's about equal to 1.5498. And we want to figure out what is the error. So what is the most that we're off by? So that's the remainder, R10. So the 10 referring to the remainder if we have only 10 things in our partial sum. That's going to be less than or equal to the integral from 10 to infinity of 1 over x squared dx. This will give us a worst case scenario for how much we're off by. And that's actually not very hard to compute. That's the limit as b goes to infinity, integral 10 to b, x to the negative 2 dx. So the antiderivative of x to the negative 2 is negative x to the negative first. So the limit as b goes to infinity, negative 1 over b plus 1 over 10. And so as b goes to infinity, that limit is equal to 1/10 or 0.1. So in this case, the size of the error is less than 1/10, which is not very large for just having added 10 things. If we wanted to make our estimate more accurate, we'd have to have more terms. So how many terms would you need to make sure that your error was less than 0.0001? So we know that the remainder for a general n is less than or equal to the integral from n to infinity of f of x, which is 1 over x squared. So we can find an n such that that integral is less than 0.0001, and that will be the n that we use. So find this integral. So limit b goes to infinity, integral from n to b, x to the negative 2 dx. That will equal the limit as b goes to infinity, negative x to the negative first, which is the limit as b goes to infinity, negative 1 over b plus 1 over n. And as b goes to infinity, the 1 over b goes to 0. The 1 over n is a constant. This thing goes to 1 over n. So we want to know when is 1 over n less than 0.0001. So multiply the n over. 1 is less than 0.0001 times n. Divide by 0.0001, and we have 10,000 is less than n. So we need to take n bigger than or equal to 10,000. So find the sum of the first 10,000 terms to make sure our error is accurate to within 0.0001. So let's try another one. So that last one took a lot of terms to get accuracy. It turns out that this one's going to be way more accurate. So approximate this series using the sum of the first 5 terms. So S5 will be e to the negative first plus e to the negative second plus e to the negative third plus e to the negative fourth plus e to the negative fifth. Don't find a common denominator, just get me a decimal approximation. That's about 0.578 approximately. Okay, now let's find the maximum error. We know that our remainder for adding the first 5 terms is less than or equal to the integral from 5 to infinity e to the negative x dx. And that's equal to the limit as b goes to infinity, integral from 5 to b e to the negative x dx. Now an antiderivative so we got the limit as b goes to infinity. An antiderivative of e to the negative x is negative e to the negative x, evaluated from 5 to b. So that's the limit as b goes to infinity. Negative 1 over e to the b plus 1 over e to the fifth. And that's about equal to 0.0067. So only adding together 5 terms, we already had pretty good accuracy. The accuracy will be better if the terms in your series decrease more quickly. So 1 over n squared does not decrease as quickly as e to the negative n does. And the last question is to find a capital N such that the partial sum S of n is within 5 decimal places. So what that means is that you need your remainder to be less than or equal to 1, 2, 3, 4, 5 zeros and a 0.5. And that will allow you to have some kind of rounding error, but that will get you 5 places that are matching. So you want Rn, which is less than or equal to the integral from n to infinity of 1 over x squared plus 1 dx. You want that expression to be less than 0.5 zeros and a 5. So that's the same thing as the limit as b goes to infinity, integral from n to b, 1 over x squared plus 1 dx. The antiderivative of 1 over x squared plus 1 is inverse tangent, evaluated from n to b. See the limit as b goes to infinity, inverse tangent of b minus inverse tangent of n. And as b goes to infinity, inverse tangent of b approaches pi halves. So that's pi halves minus tan inverse of whatever n is. And you need this thing to be less than 0.12345 and then a 5. So solving that, first I took away the pi halves, and I have negative inverse tangent of n is less than, of course I approximated, negative 1.570791. Then I divided by negative 1 and got that inverse tangent of n is bigger than 1.570791. And then I applied tangent to both sides and found that n was bigger than 1255.76. Now n refers to the number of things we add together, so in this case we always have to round up. So n is bigger than or equal to 1256 terms. So even if that had said 1255.1, you would have to round up to the nearest whole number.